this semester's IQS seminar. As our first speaker, we have Guy Waegell. He's our local member, and I'm happy to.
Thank you, Vivek. All right, thanks to Vivek and Andrew for inviting me to do this. This is work that I've been chewing away on with Emily and Kelvin for, I don't know, the last 6 or 8 months, something like that. And I'm excited to finally present something about it. So the Generative Programs Framework is a unified way to present any and all physical theories that explain the empirical data that we observe. So the idea of the framework is to give a single coherent way to express any theory that reproduces the data. And there's kind of a fundamentally operationalist bent to this, because what we're saying is that if you've got any coherent program that gives a logical description of how the data that we observe arises, it's just as good as any other one. We're not going to, at this stage, we're not going to be playing any kind of favorites about which explanation you give for the empirical data. As long as it produces the same stuff that we observe in a lab, or if you're talking about a particular model, it produces the data that follows from that model, it's as good an explanation as any other one. And we'll get into reasons why you might prefer one or another later on. So what is a generative program? So it's a partially ordered set of internally consistent instructions. The idea is that you start with absolutely nothing, and you have to give instructions in an ordered way. If some instructions depend on prior instructions, then the ones they depend on have to have come first in this ordered set. But if there's no dependence, then they don't have to be in any particular order. So the idea is that we start with nothing, we give these instructions, they're executed in some order, and that generates all of the data. And what we're saying here is that unless you've given at least this much information about how your proposed theory or interpretation works, you really haven't said enough for it to be taken seriously. This is the minimum to say that you know how your theory starts from nothing and gives you all the data that we expect to see. If it's missing any components, then it's not really going to be able to do that job. And so we really can't think of it as a physical theory. Now, one of the crucial things to understand here is that these instructions are executed in some order, but that order doesn't necessarily have anything to do with space and time. It could happen outside space and time. It could be before space and time are defined. We're really starting with the description of the theory. So you can start by defining metaphysical entities that aren't in space-time, and maybe use those to build up other metaphysical entities that aren't in space-time, as long as eventually you get to all of the empirical data, and your story is a program that is consistent enough that really, if you wrote the code and pressed run on a computer, it would execute and it would produce all of the correct data and maybe print it to your screen or put it in memory, whichever way you want to think about it. So this is sort of the standard. It has to be such that if you were to troubleshoot or debug the thing, it would always work. You would never have your program crash. That's kind of the standard we're taking for it to be logically consistent. And once you have this idea, the information flow in a program can always be represented by a directed acyclic graph, which I'll just call a DAG from now on. So whatever these entities that you're defining are, those are going to be the vertices of the DAG. And if the descriptions are being built up where I'm building up a new entity using information about prior entities, then I'm going to have arrows that go from the prior entities to the new entity in the DAG. And so this is kind of to give the basic introduction to this idea. So this first thing says what I just said. If you've got an arrow from one vertex to a second, that means that the entity at the second one is defined using information about the entity at the first. And in a DAG, there are what we call original vertices. These are the ones that have no arrows going in. They just are places where information starts. The original vertices have to just be specified as some fixed quantity that appears in the program. They don't come from anything prior. And so you're free to give a program, kind of the most simplistic example of a program would just be, here is a list of all the empirical data. It's just all generated. There's no internal structure at all. It's not a very satisfying program, but it literally just declares all of the empirical data. If you're familiar with programming, this would just be like declaring a whole series of variables and then writing them all to the screen. You wouldn't expect there to be any internal structure. But in general, we're going to want a little bit more structure than that. So I could just say, here is a physical quantity. I'll just declare it as a vertex. But in general, I'm going to want functional relations between quantities. And so this is an example where, let's suppose that I have this bold C. I'm using the bold roughly to imply that things are empirical. They're going to correspond to something that someone could observe. So this bold C would be empirical data, which might have physical units, some characteristics. And I want to be able to get that out. So I'll define first a number space. Again, there's kind of an analogy here to computer programming. I might have to define the space of integers or something like that. And then given the space of all possible integers, I'll just use a selection number, which is just some real number between 0 and 1, which has a one-to-one mapping to all the numbers in my number space. So by giving this selection number, I will have picked out from the number space this particular number, which has a physical dimensions maybe. And the reason that we need to do this is that if I want to define a function that acts on a number on one of these quantities, then I need to, and that's what I'm going to do with this sum function here. I need to do something that connects the function to the variables that I'm going to feed in, the inputs of the function and the outputs of the function. So I'll define a number space, and then I'll define the space of all the functions that map from one element of the number space to another element of the number space. I'll use a selection number S to pull out this particular function, the sum function, and then I can express that whole thing as a condensed vertex. So a lot of the time we have this sort of background assumption that to make things coherent, I have these number spaces and these selection numbers, but going forward, I'm going to omit these details. So when I give an original vertex like this, it's assumed there might be some number space structure that goes behind it. And when I give a function like this, it's going to be similarly assumed that there was some number space and I found some space of functions and picked one out.
What do you mean by all functions?
I mean, any function that you can define that gives you
definable. So they're all definable functions.
Yeah.
Okay.
Yeah, I mean, that's part of what we're trying to do here is to say that everything that you're going to use, it has to be well defined. If you could not press run on the computer program, it's not going to be.
That was the question. Okay.
Yeah.
So well-defined is something else than computable.
Say it again.
Well-defined is different from being computable.
What do you mean?
Well, I probably mean computable, but the idea here is to be so open to all comers that we might be able to accept a theory that is only defined as long as we can run the program. So that's the criteria.
Computable functions, you don't even have.
Then probably not,
right?
Yeah, probably not. I mean, I'm trying to be as open-minded to a theory. So if there's some way you can construct something that's logically coherent and ultimately results in giving the data, maybe these are precursory entities you're defining that aren't going to correspond to data. It's possible you can come up with a program that uses them. I don't think so off the top of my head, but maybe. I don't want to immediately kill off any possibilities.
No, but still the question is like, I mean, if you, how much is this based on math, and how much is there a requirement that things are computable? You mentioned that computability is important, but then you lose almost all of the mathematics that physicists use. So it's not clear to me how you want to bridge that gap.
Yeah, I think it probably does all need to be computable, but part of what I'm trying to do here is to say that if you're going to give a program, it may be one that is beyond human comprehension. There's a premise that it exists, that there's some set of instructions which generate the data, and in the list of all possible programs that do that are going to be some that are so complicated that we can't really understand them. But if you're proposing a particular theory or interpretation, then this is what you should be able to provide, is what you say is the instructions in language that we can understand. So the ones I'm going to talk about, they're all going to be computable. Everything will be comprehensible. So probably the answer is that it has to be computable, but I'm not 100% certain. I have to think about it more, is basically my answer. I'm not sure.
In the first example, you said that the selection number is a number that is going to point to some element in the number space.
Yeah.
In the second case, the selection number is pointing to
an element in the space of all functions.
Okay. And you only need that it's injective, right? You don't need that it's exhaustive too.
That's right. Yeah. Okay, so this is the first example then of a function. So I've got A as a original vertex, B as an original vertex, and the sum function is being declared as an original vertex. So I'm glossing over this other stuff that might be embedded inside these vertices, basically. But this is kind of illustrating the core idea of how the programs are going to work. If I have a variable C, some quantity or entity, and it's defined to be the sum of A and B, then I have to input to that vertex A and B and the function. Those are all the pieces of information I had to use to get this new quantity C equals A plus B. So that's the structure we're going to have for these DAGs, is that any information I had to use, be it quantities or functions, that I needed to get the value of some vertex, all of those things are going to have input arrows into that vertex. Okay, so this is trying to connect it up to some concepts that are familiar from computer science, but now let's look at what we kind of are thinking about for physical theories. So this is really looking at a physical theory, but taking a step out, or taking a step very, very far back. So this is an example of what we call presentism, forward in time presentism. So our original vertices are some initial state and some time evolution function. And we've hidden the number spaces, but it has to be the case that the initial state is something that's in the domain of this time evolution function, and the states that come out are something in the range of that time evolution function. So we have to link those up using some notion of a number space that I've hidden away here. And then we have some amount of time that passes as part of the function. In most theories, this is going to be something like an infinitesimal amount of time. And so the idea here is that there's a present state that exists. You can think of this state as being a state of the whole world or the whole universe. We'll talk about locality a little bit later, and we'll get into having to break that state up into different pieces. So if I want to find the state at a later time, the things I need are the initial state, which I plug into this time evolution function, which I evolve by some time dt. And then that gives me my new state after that time dt has passed. And then I just repeat that process. And what presentism means is that we say that at time zero, only the present is all that exists. So only the initial state exists. And then a moment later, only this state at time after time dt exists. And then a moment later, only this state at time d2 exists. 2dt exists. So the presentism picture is that we have just one state of the universe at any given time, and that the other times don't exist. This is going to work for any deterministic time evolution function. So, here in this diagram, I can talk about classical mechanics. I can talk about Bohmian mechanics. I can talk about unitary quantum mechanics with no collapse, so like the Everett many worlds interpretation. Those are all going to fall inside this basic structure. And I can take those same time evolution laws, and I can also look at the eternalist picture of this. So this just says I have a time evolution function. I plug in some boundary condition, which is informationally complete, and that generates the entire block universe. So if we're talking about sort of standard like relativistic classical physics, we would say that if you give, then our time evolution function is time symmetric. So again, if you give an initial state, from that you can generate the whole block universe. But you could just as well give a final state in the future, and that would give you just as much information and allow you to define the entire block universe. You could define a time slice in the middle. You could even give some scattered set of data points. As long as those data points are internally consistent and they give enough information to define a complete boundary condition, then I can get the whole block universe out of those. And so the idea of eternalism is that all of time exists all at once. There could still be some notion of the present that we're experiencing, but as far as the underlying physics is concerned, a time in the future, a time in the present, a time in the past, they all exist equally well, which is to contrast with presentism, where only one of these time slices exists at a time.
In your forward in time presentism, is time discrete?
Yeah, I mean, in order to give this diagram, I had to make it somewhat discrete looking, but I'm trying to imagine that this dt could be as infinitesimal as you like. Maybe we'll use a funny number space for that so that we can really get it to be effectively zero, or effectively as close to zero as we would like.
But the dark needs to be finite, right?
The what?
The DAG.
The DAG.
Oh, the DAG.
You need some kind of infinite.
Yeah, the DAG doesn't actually have to be finite.
It doesn't have to be.
Not really. Yeah.
Okay, so but then
specify how it works.
Then nothing will be computable in your, or how will you make things computable?
Well, I guess that's a good question. Yeah, so maybe if it really is infinite, then it's not really going to be something where we could actually compute it, but we can at least understand that it could run. There wouldn't, if every time I do one step like this, everything works out logically in a logically consistent way, and I don't generate a state which will now, when I plug it back into the function, will cause it to crash, I can sort of be confident that it would run even if it was infinitely long. But it would not be strictly computable in the sense where we could actually simulate it ourselves. So it's not really a computer program that we could necessarily run, but one which you could imagine on a computer with infinite resources you could run. And it wouldn't, again, the program wouldn't have any internal conflict, like a syntax error, which would cause it to crash.
So it could be interesting to formalize the notion of computability you need to make that work.
Yeah, I haven't really thought about that angle on this. I know there are connections to computer science. So
in this case, you have a repeating structure in your DAG. So you could
unfold that back down into a program that just describes one step and repeat the step. It's just an infinite loop.
Yeah, that's basically right.
So
Yeah, but these kind of recursive programs give you only a very small kind of fraction of.
exactly, but that's what he has. I mean, let's
Yeah. We can talk about it later.
All right. So why do we want the GPF? There are a bunch of reasons that I'll go through by the time the talk is over. But this is one of the main ones that motivated me to develop this, is there are a number of interpretations that are out there which don't really meet the standard I'm talking about. There are some vague details that aren't specified. There's some logical inconsistencies that are there inside the theory as it's stated. And my hope is that by putting this out there, we can motivate the proponents of these theories to actually get a little bit more serious about what they mean and tell us the details of how their program should work, so that we can really then evaluate that program and compare it to other ones. I'm not going to name names here or go into the details, but there are a handful of theories that I have objections to, and I'll talk about some of them as I go through. Okay, so now what about operationalism? So an operationalist can still use a program. I know that the way I've been describing it, it sounds like, we're talking about something that generates ontology, and that is in fact what we're really going to be interested in. But if you've got a program, it doesn't actually belong automatically to an ontology, it doesn't correspond to an ontology. It might just be a program that an agent has, which they use to make predictions about what's going to happen next. So it could be something that has nothing to do with what's really physically going on, what's metaphysically happening in the world. It could just be literally a tool that someone has that they use to make predictions. But if that's all it is, then I could talk about a bunch of different ontological programs that are supposed to be the real story of how things are generated. And there's a huge class of them that generate the same empirical data, and they have all different properties. And if you're an operationalist, what it means to be an operationalist is that you've got the data and you can see that there are some regularities, which I'm going to call laws in the data, things like F equals MA that seem to be true in the empirical data we look at. But you have no grounds to choose between one program or another. If you're an operationalist, all of these programs, by definition, they all produce the same data. So you simply have no argument as an operationalist to say, I like this one and I dislike that one. It's only going to be possible to make distinctions if you say that the program you're talking about is the ontologically true program, and then the mechanisms that are happening in that program, whatever functions are being called and with inputs and outputs, those are the real physical mechanisms. And what I'm going to talk about later on is this is how we can really define a notion of what is physical. It has to do with looking at the ontological program you're talking about, the one that really describes what you're claiming are the actual true mechanisms that reality is using to generate the data. Okay, so this gives us a way to define a rigorous definition of realism. So there are a bunch of different definitions of realism that are out there in the literature. A lot of them are tied up with some notion of causality. Can't really define a notion of realism without some notion of causality. But included in the programs that we want to consider are ones that have no definition of causality. They simply are completely acausal theories. And if we're in such a case where we have no causality, we can still talk about the structure of the reality by giving this DAG of ontological priority. So we're going to use this term ontological priority as something that's more general than causality. So when I say that something is ontologically prior to something else, I mean that there's an arrow that points from the first thing to the second thing. Prior in the sense of the order of execution in the program, but not prior necessarily in any temporal sense. So we have these diagrams that have arrows going forward. So this is ontologically prior to this. That's what we mean by the arrows. Okay, so as I said, I want to talk a little bit more about
that. Select the independent variable and make ontological prior in this sense. It means that you have identified the number of independent variables. The value of the other variable depends on the variable of the independent one.
Yeah.
What you're doing, in fact, is fixing the independent variables.
Yeah. Those are the things we're calling original vertices, are the independent variables. Yep. And that the fact that they're independent is important. I'm going to come back to that. Okay, so as I said earlier, if we want to talk about, we want to like zoom in a little bit on a theory and say whether or not the theory is local in space-time, now I have to define states that are at different events in space-time. And this is a model for a theory that will be local and could obey local causality if the ontological priority arrows you see here are defined to be causal arrows in that theory. So, I mean, sort of the generic case is that this would be a picture of local causality. So the idea here is that I have separate states at different events in space, which collectively, like this whole row here, describes the state at time t. So that would have been maybe the whole initial state in my previous diagram. But now I want to assess whether or not the evolution that's happening between entities in space-time is actually local. So each of these would correspond to some empirical data that could be seen if I'm an observer who's at this particular location and time. And then if I want to know what's happening, say, at this event up here, I want to know that the information I need to use to get that is going to be, again, our whatever our time evolution step is, whatever our function is, but now it's going to be a local evolution function. What makes it local is that it's only able to take these three prior states as inputs. And really, there's an infinite number of states in between. But the point is that this spans the past light cone of this point. And so what local causality is saying is that all the information about the past state that I should need to define what's happening at this state is the information about the states in the past light cone. And that actually implies that these states have to be separable in the sense that this state has to be separate from this state, has to be separate from this state, because if these two states here were one entity that I could not separate, then the information about this one would include information from over here, which is outside the past light cone. So I'm basically forced by the premise of locality or local causality. Again, if you think these arrows describe causality, to come up with a theory that is separable that has a separable state in the sense that I can give a description at one event, which is separate from a description at a neighboring event, which is separate from a description at a neighboring event, and so on. So if I want a local theory, when I zoom in on the time evolution, it has to have this structure. Or at least one that's very similar to it. We could actually imagine one that does not actually require that you go from one present time slice to the next. So you could actually have an arrow that goes directly from here to here and skips this one in the middle. This would be like a non-Markovian local causality. It's possible you could have a theory like that. It would still obey local causality. So this is just kind of like a base example. Okay, so the point of showing that particular diagram is that physically real properties of a theory like locality, superdeterminism, causality, fine-tuning, contextuality, these things can only be true or false of a program that you take to be ontologically true. There's no operational claim you can make about these things because the operationalists, again, they have no way to choose between one program and another. And I can give you one that's local and one that's not, or one that's superdeterministic and one that's not, that generate the same data. So if you're an operationalist, you have no grounds to say that your theory is local or non-local. That's what I'm saying here. So really, the idea of picking out a program and saying that it's physically real is that now I'm saying these are the actual mechanisms that are involved in generating the data. And now I can literally just look at those mechanisms, and the question, is it local, will be a yes/no question. The question, is it superdeterministic, will be a yes/no question, given a particular definition of locality or a particular definition of superdeterminism. And that's another thing, is that there are a few different definitions of locality that are out there, and that's fine. Those, all of these things are kind of like separate heuristics that I can use to evaluate a program once I've got it. So maybe it's not local by one definition, but it is local by another definition. Either way, those are going to be yes or no questions. It will be unambiguous what's going on. So there won't be any confusion about whether the thing obeys this particular heuristic or not. So that's one of the virtues of the GPF, is that I can give a bunch of different programs, they all generate the same data, and then we can come along and apply our usual heuristics relating to locality, superdeterminism, contextuality to say, this program is better than this program. I have a reason to reject this program. I like this program more. We started by saying that any program that generates the data is equally good, but now we're going to come along and start adding, what are essentially subjective philosophical qualifiers. Like we as people want theories that have certain characteristics. We want theories that are simple, maybe. So we have Occam's razor as a heuristic, or we want theories that obey Leibniz. I've lost the the words here. Thank you. Identity of indiscernibles. So it might be the case that you have a program where things which are indiscernible nevertheless have distinct identities. That's possible, but you might want to reject programs like that. So that's the point of this, is that if we start off being neutral, we can look at all of these programs side by side and then evaluate their properties separately and decide if we like one or another. Okay, and then this is really driving home this point. If I've got a program that I say is ontologically true, that defines what is physical. So the empirical data, we're all going to agree that the empirical data are physical, but there might be other relations that connect the data up in some way. And some of those relations may correspond to what's happening with the actual physical mechanisms of the program, the things that really had to be input to generate the output. And some of them might be incidental. They might just be facts that are true about the data, but they didn't actually correspond to any mechanism that was there. They come along as byproducts. And so those entities, those relations, they don't necessarily correspond to any physical mechanism. And so we won't call those physical. So by looking at a program, we can now delineate between which mechanisms are actually the physical ones that were involved in generating the data in the ontology, and which other relations we can see in the data that just happen to come along as a byproduct. And again, once you've got a specific program that's laid down, you can see clearly which those two things are. There won't be any ambiguity. All right, and now just to illustrate something we can do where we talk about theories that don't necessarily obey the forward in time story about things. We have a couple of these all at once theories. So this first one, we have a time evolution function. It may or may not be time symmetric, but we take that time evolution function and we just consider every input in its domain, and we generate every output. We generate all in its range. We generate the complete history according to this time evolution law of the entire universe, and we generate every possible history given the possible values that you could put into that function. And only then do we come along with a selection number and pick one out, and then we just generate all of the data in space-time all at once.
So also, I do not understand what does it mean all possible histories. With a domain that is numerable, the all possible history is not countable. So what does it mean all?
Well, we could be talking about a simple model. So so for example, if we go back to the sum function, if we have like the sum of real numbers, then the case of all possible histories would just be that we have our time evolution function is the sum function, and we consider all possible inputs and outputs to that function. And then we just pick out one case. So we pick out one particular case. Or maybe a better way is just to go to classical mechanics and say, given classical mechanics, I could plug in an initial condition. Well, now let's just consider all possible initial conditions. And then from each of those, we would generate an evolution and a whole history. And then we'll just pick one of them out after the fact. The reason to do this is that we, sorry.
A possible condition is a value of a real number. So I have uncountable many possible initial conditions.
Yeah, there could be.
So I have the power set of an uncountable set is even more than uncountable.
Yeah.
So I simply do not understand what all mean in this case.
Well, it can be this uncountable set, as long as we define the selection number to be one that has a one-to-one mapping to whatever the space of possibilities is, then we can select out one.
One do you really inject?
I think so. Yes. Yeah.
Because
I mean, each one indexes a particular history. That's what I mean. So,
but that's different. Indexing means that you have a number for every history, but you only need to have numbers. But you only need to have the two indices are not pointing to the same function.
yes.
But you might have functions that are not indexed at all, because at the moment that you ask every single function is indexed by some number, then you need to have a huge set of numbers that you might not have.
You can't number more than real numbers.
Well, we're trying to generate something that's consistent with some model. So if I need a particular function, then I need to be able to index it. And if I don't need the function, then I guess I don't need to be able to index it. So the things that might be necessary as inputs, we'll have to be able to index.
So you have not.
I admit that this thing about the selection number is pretty abstract. I know that there are. I chose the real numbers from 0 to 1. At least it's a continuous set, but we might need some other kind of selection numbers to index things.
Not unspecified.
Okay, yes, it's that.
So what you are saying is not the set of all possible history, is the set of each one of them.
Yeah.
So
Yes.
take one, you can take,
Yes.
go there,
Yes, okay, yes.
not all there.
Yeah, I think that's right.
Okay.
So yeah, so the purpose of this is really that because I picked everything out about the entire history across all of space and time, I've picked out a block universe, but then I just dump all of the information, all of the empirical data into the block universe at once. And there's no sense of causality here. There's no sense in which one piece of data that's there in the block universe came before another or had to do with creating the other. I created all of them sort of wholesale before I put anything in space-time. That was kind of the virtue of doing it this way. And I made a point to put the selection number in here, but otherwise, I'm back all the way up to here. This looks pretty similar to here. I didn't specify it, but there would of course be again some kind of selection number that goes here as well. I somehow have to pick out one possible boundary condition out of the set of all possible boundary conditions. It was just hidden away in here. But again, there has to be a number space that says this boundary condition is an acceptable input to this time evolution function. And then that between the two of them, they'll generate this block universe. So we always have these selection numbers that are pulling something out. I should say we don't actually have to have them. It is perfectly possible to define a program that just says these things exist without any priors. There's a reason that those types of programs are going to be undesirable. It's again just one of these heuristics. So you can give programs like that, but I'll give an argument later on for why we tend to want to avoid them. And that's why I started off by defining these number spaces.
Okay, can I just ask again? So if you say program, you mean something that is computable in the traditional sense of computability theory, or you mean something else?
No, I don't think I mean something that's computable in the traditional sense. I mean that what I said, in this definition right here, that it's an ordered set of internally consistent instructions.
Okay, it's a program in that sense.
That's what we mean.
It's running outside of time, so it doesn't matter if it takes infinite time to run the program because it's not occurring in time anyway.
Yeah, this is this next point, is that the execution of this program, it's really independent of space and time. In some cases, you can give a program where things are happening in space time. And so like the local causality or the local, forward in time evolution that I showed here is kind of a case where you would. But in general, you don't have to. And so
my next question would be, do you have a formal notion of computability that would correspond to that notion of program?
I don't know. I haven't thought about the computability angle much. It's definitely worth developing it more, but I haven't thought about it very much. So, yeah, there's a deep analogy here to computer programming, and so I'm sure that can be pushed further, and we can understand what the connections are better.
Yeah, I think because I know some of the programming standard kind of stuff, right? I would be very interested in kind of understanding what of that technology methodology could be applied to your setting.
Yeah, I'm happy to discuss it with you more. Do you have a question, Neil?
Yeah, so I understand how we can say that there's DT and this involves time, even though it's a bit tested because time works. But if you're putting it in a computer science framework, Dr. Kirk said, I no longer know how to think of DT as a time step. Because we're saying this gets small, so I don't understand how to go from one state to the next if we're really not evolving any time at all. DT is
well, it's not going to be actually zero, but I mean, like if we're talking about the time evolution functions that we get in classical physics or unitary quantum mechanics or Bohmian mechanics, DT could actually be quite large. You have a unitary evolution law that tells you like how to evolve the thing arbitrarily far or to a far away future time or a very small one. I think that we tend to prefer a theory where DT is small because maybe it's only as small as like the time between measurable things that we can see in a lab, or maybe it's like a Planck time or something like that. It may have some finite value.
Okay.
And all of these laws, well, I mean, again, you might propose laws that really don't work, where you plug in even an hour and you see what happens an hour later. But you could, in principle, have the theory built out of laws like that.
Okay.
Certainly, all of the standard cases that we're talking about, they don't require that you have a very tiny time evolution like this.
So by DT, you don't actually mean infinitesimal. You mean a time unit smaller than we can measure.
Yeah. I mean, if it's smaller than we can measure, then it will reproduce all of the empirical data that we see, like no matter how often we look.
But you're not making a statement here about all the empirical data we can see. You're making a statement about the nature of time. And so
Well, again, the only job that the program has to do is generate the empirical data.
that's all it has to
That's all it has to do. That's the only condition.
Yeah,
Is that
but we're trying to say that, look at diagrams that represent the actual physical mechanisms, and you might have in your mind that the physical mechanism is actually continuous in time, in which case you need to be able to represent that.
yeah.
And there might be a framework that allows you to evolve these.
Well, this is another thing, is that there might be another way to write down a DAG that captures the idea of continuous evolution better.
I think
This kind of unpacks it so you can see what the ideas are.
the
But
comment on that is, it sounds to me like you need to adopt a richer framework, like something from category theory, and that you should talk to. DAGs, I don't think is going to suffice for everything you need to do.
that may be true. And actually, something that Emily and I talked about early on is that we chose DAGs because there are no loops, and so you can avoid a lot of paradoxes, but there are actually some special types of loops you could have which also don't give you paradoxes. And so we want to generalize this to include those. So there actually could be certain types of cycles that are allowed. So there are several ways to generalize this beyond what we're doing here. But I think this at least gives this is enough to get all the flavor, all the core idea of what we're trying to do. And the whole point is that, I'm going to give you some example programs, but you could come up with other ones too. There's no restriction that these are the best ones. Many of them are extremely oversimplified. And so we expect that there's some deeper story going on. Okay, so let me continue with the all at once theories. So another one we could look at, this one actually does have an order of time. So this is an initial state in space-time, a final state in space-time. We have a time evolution function. This is just going to be unitary quantum mechanics. And this, between these two pieces of information, they define this counterparticle reality that Yakir Aronov has been trying to develop for a number of years. And so this gives you a whole ontology. It's got weird particles, negative copies of particles, imaginary copies of particles. But it is a complete non-contextual story of what happens throughout space and time. And as long as this final state doesn't have any macroscopic superpositions in it, then it will be consistent with everything that we observe. So this is just another example. So the idea here is that time is going forward, but in order to generate the counterparticle reality, this is a retrocausal picture. So I have to take as inputs the initial state and the final state. So information about the past and information about the future and this time evolution function. And then I'm able to generate a kind of block universe, which is this reality that fills in all the time in between. So that's another example of a kind of theory. And the reason I put these in here is just to really emphasize that these programs can be executed really independent of the normal order of space and time. In this one, there is no space-time at all until we get to this point and put everything in. And in this one, we have information flowing both backward and forward in time to generate all of the data. And we can have more abstract cases than that, certainly. Okay, so now I want to get into talking about non-deterministic vertices. I was talking before about those being deterministic functions. Strictly speaking, they don't really have to be. We can go back to those diagrams and modify them to include non-deterministic functions as well. We just kind of bake them into the time evolution law. But we've made it sort of an informal rule that if you have random numbers, then they should not be hidden away. You should show where the randomness is coming into your program explicitly. So this is how we would get a random value. So again, this is like some empirical value with units. There are a couple of steps here. So I define a number space. I then define all probability distributions or each probability distribution over that number space. Then I use a selection number to pick out a particular probability distribution. So what's going to be happening when we talk about quantum theory is that it will be really the past quantum state that goes in and figures out what this probability distribution is going to be. So it'll be like a Born-Rule distribution if we're talking about quantum mechanics, but this is more general. And then once I've got this number distribution, I use some now uniformly random selection in 0 and 1. So before it was just some selection number, I just put it in there with a value. But now I'm saying that the program pulls it out from 0 to 1 completely random with a uniform distribution, and then uses that to pick out an element of this probability distribution. And then that's what gives us the value that we get as our empirical data. And so most of the time I'll ignore this number space stuff here at the bottom. and the space probability distributions, and we'll just have these diagrams, and the prior coming in here will be something about a past state. This is how we can formally define these original vertices to be random. So in this case, I usually will not just give this R vertex as a random vertex. I'll show at least what the probability distribution was in the DAG. Okay, so now let's update our presentist theory to include these random events happening. So now I have an initial state, and to get the state after some time, I have to first use the initial state and the time evolution function to generate some probability distribution. Then I use a random number to sample out of that probability distribution. And then that contributes to what the new state is, along with some information about the past state and the time. So this could describe quantum mechanics with collapse, for example. I can have like this over here describing my unitary evolution. And then if there happens to be a collapse that happens during our time dt, then we would also have some Born probability distribution that comes from quantum mechanics. And then we would use this random number to select out the outcome. Somehow nature determines one outcome from the distribution. And then we would just repeat that process. And again, if this is presentist, then this state exists first, and then we do this evolution, and then this state exists, and so on. So this is how we would incorporate non-determinism into our theory. And what I'm going to do next is go through some examples of Bell's theorem. I'm not going to review Bell's theorem because I don't really have time to go through all the details. But what I'm going to show you are some DAGs for different programs that explain the data in Bell's theorem, and we can actually look at some of the properties of these different theories.
Sorry, I understand what perhaps is not clear. You are, in some sense, reducing a non-determinism to random, to probabilistic, but non-deterministic.
That's what he means.
Yes.
He means probabilistic.
I mean probabilistic, yeah. I'm going to come back to this point.
Non-deterministic means that evolution can cross.
I will come back to this point, and maybe we'll disagree strongly when I make a case about this. We'll see. Yeah.
Okay.
Okay. So if you're not familiar with Bell's theorem, we prepare an entangled pair of particles, or it could be a more complicated entangled state. But for this one, I'm going to use this state for all the examples here. Correlated Bell state. You send one particle off to Alice, the other one off to Bob. They're at space-like separation from one another. I've made it so that Alice does her measurements before Bob in this particular reference frame, so that we can have kind of clear notion of the flow of information through time. And these quantum states describe everything in this theory, but they're not really anywhere in space-time. So I've drawn them just going straight out the center because they don't really have a location in space-time. A quantum state is sort of abstracted out of being in a particular place. Actually, sorry, it has a location in time, just not one in space. Should be more careful. So I prepare this state, and then over here, I have Alice making a free choice of her measurement setting. So I'm letting her free choice be another kind of original vertex.
That is an enigmatic remark.
Oh, I'm really running out of time fast? Yeah. Okay. All right. So yeah. So this is our one story of Bell's theorem, with kind of the traditional quantum story with collapse. So Alice makes a free choice of measurement setting, which I represent as an original vertex. That produces a probability distribution in conjunction with the state. That's the Born rule. And then these combined with a random selection pick out her outcome, which also updates the quantum state. And then that updated quantum state determines the probability distribution for Bob. So this is the updated quantum state here, assuming that Alice measured the 0-1 basis. So that the examples I'm giving here with the numbers are for the case where she happens to have measured the 0-1 basis. And then the same thing happens for Bob. He has a probability distribution, which is now coming just from the state 0-2 that's been prepared for him for his qubit. He makes a random selection of measurement. And if the selection happens to be Z, then this is the state he gets. He just gets back to state 0. So this shows how the correlated result 0-0 appeared, and if the setting had been different, then it would have still been correlated. This just is one case example, and this shows that the explanation here is non-local, because I have some events here are actually in space-time, and there are arrows going between events in space-time over here and space-like separated events in space-time over here. These bold ones again correspond to things that were empirically observable. And so we have once we give this program for for quantum mechanics with collapse, we can see explicitly that it's non-local, which I don't think anyone disagrees about. So this is just kind of recapping a standard example. We can also look at unitary quantum mechanics. So this would be like many worlds or Bohmian mechanics, where we have a universal quantum wave function which never collapses. Maybe it's supplemented by some other information. And so in this case, I'll put in the states for Alice and Bob as well, the ready states. And so in this particular frame, Alice does her setting, she comes along and measures. That actually is just a unitary coupling between Alice's state and her qubit. So the entangled state evolves to this, where Alice is now correlated to the two qubit states. Bob is still in a ready state over here. That evolution was determined solely by Alice's choice of setting. And then from this state, we can extract out the outcomes that Alice sees. There are two different worlds. A represents her setting, and it could be any setting, and half of the world she'll see the 0 outcome for that setting, and half of the world she'll see the 1 outcome for that setting. The state's updated. So now Bob makes a setting choice, and that again just applies this unitary U2B up here, which evolves the state to this one. And now again, from this state, I can see that I've got my two Bobs having had these different experiences. And now if these are great arrows, if they happen to have measured the Z basis for both of them in this case, then another thing that follows from this state is that the 0 Alice will meet the 0 Bob, the 1 Alice will meet the 1 Bob. So there's effectively two worlds here in this state, where I have, one where I have 0, 0, one where I have 1, 1. And if I was talking about, if I want to look carefully at what's happening, I already really have these two distinct terms, these two distinct worlds in this state. And so if they had measured 0, I can see that this Alice with 0 is in the same world as this Bob with 0, and this Alice with 1 is in the same world as this Bob with 1 already, by looking at the state that describes them. And now there's an issue about switching to another frame here and the narrative changing, but I'm going to skip that for time. So this is an explanation of how we get all the empirical data that's observed, even by multiple observers in different worlds in the unitary picture. And if I had Bohmian mechanics, I would have a hidden variable which picked out a particular one of these two to be the real one. And the other one would be an empty wave packet, it wouldn't really exist. Okay, local many worlds, this is my pet theory. So this one is Lorentz covariant, it's in space-time. Again, you prepare the state. I have Alice making a choice of measurement setting. This probability distribution really becomes what I'm calling a proportionality distribution. So there end up being many copies of Alice. Half of them see the 0 outcome, half of them see the 1 outcome, but they're all there in space-time. The same for Bob, half of them see the 0 outcome, half of them see the 1 outcome, but they're all there in space-time. And then when they get together, they're carrying around this information about the state as a local internal memory. So this one is obeying my relativistic causality diagram that I had before. So this information is carried along here, it's carried along here, it gets updated to this, which is carried here, it gets updated to this, which is carried here, and then when we get to this meeting point at the end, it's updated to this state, and now I can read off the proportion of joint distribution, or the joint proportions for Alice and Bob, and I'll see that half of them get 0, 0, and the other half get 1, 1, again, only if they had measured in the Z basis for this case, but it works out in general for other bases as well. So that's a local explanation. Here's a superdeterministic explanation with intentionally silly goblins to really bring out the sort of conspiratorial nature of this type of explanation. So in this case, I have a magic goblin way in the background. He's going to prepare something which dupes the Bell state we want. So he's going to do something totally different that actually allows there to be a local explanation, but he'll change it up every time so that the statistics you see in the lab will always be the same as what you would have gotten for the Bell state. So on one particular run, the goblin goes into the past of Alice and enchants her to always choose the setting Z, enchants Bob to always choose the setting Z. If they do something funny with, some special way of choosing their settings, then whatever apparatus they're using or whatever other people they use to help choose the settings, they're also affected by this enchantment. So you just have to go back far enough in space-time to do that. And then the preparation, you think you're preparing the Bell state, but actually you're preparing this 0, 0 state this time. And it could have been the 1, 1 state. And half the time it will be the 1, 1 state if it's going to be the Z basis. So then the 0 and 0 get sent off to Alice and Bob. They choose their settings, which are just going to be Z. They're forced to be Z. And then they see the outcomes are 0 and 0, which are correlated as they're supposed to be. So this is an explanation which obeys local causality as well. But Alice believes that she has this freedom to choose any setting that she wants, and she's wrong. She's been forced to choose a particular setting on this particular run. And only by having her forced setting be correlated to this state that was actually prepared, am I able to guarantee that the correlation will always be obeyed. But there is a way for that to be done. And there are plenty of other versions of superdeterministic theories you can come up with. But again, this is a viable local theory that explains the data. You might have reasons to dislike it, but it works just as well as any other. And an operationalist has no grounds to reject it as compared to the other ones. Okay, this is what's called the zigzag. So this is a retrocausal explanation. I'm going to go through this one quickly for time. So I have a source that prepares my state. It actually is going to be the Bell state. What I send off here is just the reduced density matrix of this state. And so this determines a probability distribution, which is just 50-50 for any setting Alice chooses. Supposing that she happens to choose the Z basis, then she could collapse to this outcome with 50% probability. And so let's suppose that she does collapse to this outcome. This information gets sent backwards in time, back to the source event. These two S's describe the same event in space-time, but they're two different vertices in the DAG. Otherwise I would have a cyclic loop here. So again, where the vertices in the DAG are, they don't have to be fixed to space-time in any rigid way. There's new information here that was not here. It depended on these things being ontologically prior to what's happening at S2, but not S1. So now I take Alice's outcome, I project the state and update it, and now that gets sent off to Bob, and he just does whatever measurement he wants. If he happens to measure Z, then he'll find this same state 0 again, and the correlation has been obeyed. So this is like the Parisian zigzag. This one's also consistent with the mentaculus, because a choice that's made in the future changes something microphysical and unobservable in the past and produces the correlation in that way. So if you want to talk about that theory, then this is an example that would work the same way. Okay, so now I want to get to kind of the crucial point here. So I've been talking about these original vertices where we just kind of put in values that are well suited to some particular program. But I want to talk more about what we mean by saying these original vertices have no inputs. So the idea is that we start with absolutely nothing when we give a program. And when I give an original vertex, there's really no context that connects it to other vertices that might be in the DAG already. The only things it's going to be connected to are those that are downstream, arrows that point from that vertex down to other ones. So the value, if I've already got some stuff in the program and I bring in along an original vertex, if it's original, it has no context or information about the rest of the program that's already there, which means that its value relative to those things has to be completely arbitrary. It can't actually be related. If it was going to be related, there should be an arrow that brings in information to that vertex. So it's completely arbitrary, which is also to say that it's random. So what I'm actually going to argue now is that all original vertices should be random. There should be no relations between the value of an original vertex and another original vertex, or the value of an original vertex in any other part of the DAG that's not downstream of it. And so really, this is the critical claim here, is that to be an original vertex is to be arbitrary, is to be random. Really the only kind of original vertex that we're actually allowed to have properly is a random one. So this is why I had to define those number spaces earlier on. If I didn't define the number spaces, then there was no reason to think that a variable that I give to be the input to a function and the function would actually fit together. It could just be, I try to plug in like an integer to a function that only takes doubles, and the program crashes or something like that. Yeah.
When you say random, you fix a probability distribution?
I use the uniform 0 to 1 probability distribution, but I mean, I'm trying to not fix a probability distribution. This is sort of like maybe it's like an even more general concept of random. I just mean that the things have to be completely unrelated to each other.
Why don't you say just non-deterministic instead of random?
Well, these words have slippery meaning, and I'm gonna come to that in just a moment. So yeah, I'm gonna
They're
talk.
very different, right? Non-determinism and probability are totally different concepts, at least in my world.
Yeah, I'm gonna argue that there isn't actually any difference when you get to this level of abstraction. That to be arbitrary, to be unrelated is to be, they're all the same thing. That it just means that one thing has no information that pertains to the other.
Like, suppose you have a computing device and you have an input. It makes a huge difference from a computability point of view, where the input is selected according to some probability distribution, or whether it's selected non-deterministically. It has a huge impact on lots of things that you do with this device, how you analyze it.
I'm actually not even sure that I understand what you mean, what the difference you're talking about is. Like, I mean, if I had a particular probability distribution that I've already programmed in, I would still have to use something to sample from that distribution, right? Some seed of non-determinism. I'm not sure what else you would call it.
You don't sample. Sampling is a concept that is not related to non-determinism at all.
Okay, but if I have a probability distribution and I want to pick out one element, how do I do it?
You sample, yeah.
Okay.
But that's different from non-determinism. When non-determinism, you don't sample. You just universally quantify over everything that's possible. That's a very different concept.
Okay. I think that the concepts are going to get mixed up in some way here. That's part of what I'm trying to show here, is that that if I'm trying to define this program from nothing and I have to define a new value with no context, then I guess it has to be non-deterministic, because it has to be just, I mean, literally I could put absolutely anything that you can imagine there. It has no relation to anything else. There's no reason to think that it will be constrained in any way.
Yeah, but random variables are constrained by their probability distribution.
Yeah, so this is going to come sort of, that's why when I talked about randomness, I defined probability distributions and I used that little R thing to select it. But the question is, where does the little R thing come from? Where does the selection number that I'm using actually come from? And I'm saying that there's absolutely no context to connect it to anything else. So even if I don't define a probability distribution, any original vertex I give, there's nothing that should be connecting it to anything else in the DAG. And that's actually the point that I'm going to get to right here, is that if I do have an original vertex and it's related to some other part of the DAG that's not downstream, that's what we're going to call a fine tuning. It means that there's a relationship between these two entities which does not appear in the program, in the DAG. And so there's something which sort of, there's some relation which begs for explanation, but the DAG is missing that explanation. And so we'll call that a fine tuning. It also suggests that there's some other larger DAG I could give in which the vertex will no longer be an original vertex. There will be input arrows that go there that explain how the thing is related. Okay, so I'm getting close to the end here. I know I'm over time. I'll try to wrap up as quickly as I can here. So again, an operationalist uses a program. It's just a tool that they use to make predictions. I'm going to go quickly here. So what this means is that every agent has to use a different program. Since for each agent, the empirical data is what they see, and there are programs that are going to have the other agent as part of the physical world, and ones that have the other agent as external to the physical world. A given agent can't tell, so the program they use has to be agnostic about that. Those are both viable explanations of the empirical data. So each agent is effectively forced to use their own little version of the program to make predictions. So that's an issue for operationalism. If the agent is outside the program, then the empirical data they receive is a terminal vertex, and the intervention they choose is an original vertex. And so the fact that those are supposed to be related, the agent is supposed to be taking in information from the DAG and then making decisions which are related to their past experiences, that's actually already a fine-tuning problem. It looks like this, that I have the agent getting empirical data from the world, and then here's an original vertex where they make a chosen intervention and they do something to the physical world. So, in operationalism, the agent just has a little toolkit that they're using to make predictions. That's something that they've got possession of. This is showing sort of the minimal ontology that they actually are espousing with their explanation of things. They're saying there is a physical world, and the agent is outside that physical world, outside the program. But now the fact that this original vertex is related to past states of the world and to the past empirical data, that's a fine tuning. This is an original vertex. It's supposed to be completely unrelated to anything else that's in the DAG or anything that's not downstream. So, so really, operationalists do tend to think that the agent exists and that the physical world exists. They both continue to exist. And so we can actually give a program, an ontological program, that includes the agent. It still has the agent outside the physical world. The agent can still use their tool to make predictions about the physical world, but then they actually make real interventions on the real physical world, and they get real empirical data from the physical world. So really, you know, what operationalists are really saying is they're kind of minimal realists. They're really saying that there is an agent, and I can describe the agent and the information flow for the agent. Each agent will use a program that looks more like this to make their predictions, but nevertheless, they're embedded in this connection with the physical world. And if I put them in like this, it gets rid of the fine-tuning problem, because now it makes sense that the agent, you know, got information from their own past state, from the physical world, made some decisions. This actually has this one will look like deterministic decisions, because I don't have any random vertices or free choice vertices in here. Okay, so really what the operationalist is kind of a minimal realist. They actually believe in a certain amount of ontological structure. It's the one that sort of keeps them separate from the world and allows them to interact with or to do things to the world and get information back from the world. But as far as the program goes, if they continue to exist, I can describe that information flow in the program, in this program that I'm showing here. And if the operationalists want to be a little bit more realist, they can adopt a physical world where they can imagine this kind of a narrative where there's multiple agents, all of whom are external from the physical world. If you're purely operationalist, you really have no grounds to say, like I have no grounds to say that you're actually an agent. You might just be part of the physical world that I'm experiencing. But I think that we tend to prefer a theory that makes all of us, the conscious entities, agents, separate from the physical world, kind of on the same footing. And so you could imagine that this is the ontology that the operationalists really have in mind for multiple agents. But again, the individual programs they use, you know, this agent will still have a program that treats the other one as part of the physical world in their predictions. And this one will likewise have one that treats the others as part of the physical world. But if you had this kind of a story, you could at least have some more internal consistency. So the reason I stopped to talk about operationalism and the role of agents is really to get into free will, which is, and so this connects up to the free choices that were being made in those Bell tests. I put in original vertices for free choices because that's part of the way that Bell's theorem works. I have to be able to talk about free choices in order to really discuss Bell's theorem. So there are these three major categories of free will that are out there in literature. Compatibilism is a notion of free will which is completely consistent with determinism. I'm not going to define that right now. Event causal libertarianism is another notion of free will that's based in randomness. And then this other idea is agent causal libertarianism. And this one is defined to be neither random nor deterministic. So it is supposed to be a kind of non-determinism that is not random. That seems to be something that people have opinions about. And so this is why I said I was going to come back to it. It's supposed to really come from the intention of the agent, but there's a problem here, which is that no viable formalism has ever been given that actually has the properties of agent causal libertarianism. It's like an aspirational notion of free will. It's the one we all kind of want to be true, I think, by knee jerk, but there's no actual formalism that works and does the job.
The word is deterministic, but I do not know the function. That's why
Say it again.
The word is deterministic, but I do not know the function.
Well, that's your belief, compatibilist, you're saying.
That's,
okay, yeah.
No, this is the position.
Oh, which one?
The third one. No,
the third one. No, I think that they're saying the world is not deterministic. That's the premise, is that the free will is not deterministic. You could not compute what happens next from what came before. The information to predict or to determine what happens next doesn't exist. The agent comes along and adds something genuinely new, which we would characterize by an original vertex. So this is now the argument I'm going to make, is that I'm going to say that there is no formalism for ACL. Certainly there is not one that is known. But this is the argument, that if the agent's choice is non-deterministic, which is the premise of ACL, the agent's choice is not deterministic. That means that some part of the DAG that describes the internal information flow for the agent must be unrelated to other parts of the DAG. There must be something unrelated which could not have been determined using prior information that was in the DAG. And if it's unrelated in that way, then it has to be represented by an original vertex in this DAG, which means that it's arbitrary, which means that it's random. That the value.
This becomes really important.
Yes, this is what I was saying. This is I know that the language here is probably contentious, but I think that the underlying logic, there's something to what I'm saying here, which we can hash out. So.
Sorry to interrupt, but we have to keep the 5 minutes.
Okay, I'm just about done, actually. I'm very nearly at the end here. So this is the new kind of thing about the arguments for free will. That this notion is very popular, agent causal libertarianism, but it seems to be logically incoherent. There doesn't seem to be any way to define a kind of non-determinism which is not random. Which somehow has room for this extra thing, which we would call intention or something. There's no place for the agent to really do anything. The intention of the agent to really do anything, if it is non-deterministic.
What does we mean here by random is what you're using the word random to mean arbitrary, so it's not necessarily associated with the problem of distribution.
Yeah,
So that's the confusion here.
I mean, this gets into like which definition. Like if you look up the definition of arbitrary in most dictionaries, it says random.
Yes.
So it's a matter of like, do you use a philosophical dictionary or it's all about nomenclature. Yeah. So, okay. So final point here on this is that if you keep the agent outside the program, you could still actually have agent causal libertarianism working, but then it just becomes like a case of fine tuning. It sort of says it has to be like this with the agent outside. And now the fact that these are related to each other has no explanation. But it is still so. But if you accept that it's a fine-tuned explanation, then you can still have this notion because you don't actually have to say what the information flow process inside there is. Okay, I'm just about at the end. So now, if we want to get event causal libertarianism off the ground, we can add this detail. So here's a DAG for event causal libertarianism. So what this says is that the agent state, all you actually do as an agent is produce some probability distribution. This is like your brain establishing the weights that you give to different choices you could make. You weigh your pros and cons and you come up, I much prefer this outcome. I'll give it 9 out of 10 chances and this one only 1 out of 10 chances. And then again, some random selection number comes along and actually picks out the one that you choose. So you don't really have full control. You just get to choose this probability distribution, but then something random contributes. And these two things together determine what your chosen intervention is that you act on the world. And then you see empirical data back. So, the main summary here is that the point of the GPF is that it's a means for us to bring all of these different diverse discussions about foundations of quantum mechanics and some issues of philosophy all together into one place with a single clear focus. It allows us to, to examine a bunch of different issues, which I won't read off, and get some clarity. This is just a recap of the ones I went through for the most part. And then it appears that it's impossible to consistently define agent causal libertarianism, which leaves us with deterministic or random notions of, fully deterministic, compatibilist notions of free will or random notions of free will, like event causal libertarianism. All right, that's all. Thank you for.
Very nice presentation. We have 1 minute left. Then we have to leave the room. So one quick question, I guess.
My comment is that it seems that you want something that is computable and complete and also consistent. And I'm afraid that this is too much to ask from something. I don't know, because maybe what you're modifying here is the notion of computability.
Perhaps. I think that my counter to this, not really counter, but my answer is that what I'm saying is that if you want to tell me that you've got a complete theory of nature, a physical interpretation, then this is what you have to do. This is the standard you have to meet to explain that theory in a way that I will take seriously. It may be that you can actually use relatively simple tools to describe your theory. The program framework is supposed to be so general that you could come up with really any kind of program that you could imagine. But it may be that a particular interpretation you present will be relatively simple, made out of easy to understand building blocks.
So can I resume when you say it this way, that to have a philosophical or in general interpretation is to identify a structure of your problem? That's what you say.
Yeah, I think so. I mean, if you're talking,
I am a realist. Okay, good.
Yeah, yeah.
What does it mean? The structure.
Yes, that's right. Exactly. Yeah.
Okay, just
Out of time.
again.